It is a great honor, a great pleasure for me to introduce our lecturer, Professor Richard Ellis. Professor Richard Ellis is full professor at the Caltech Institute at Pasadena, California, still chair. He is an observational astronomer observing remote universe using huge telescopes and analyzing the observation, the results. He just tries to determine or to write the history of the universe. Where do we come from? How is it so that we're here where we are? The beginning of his work at Oxford University, where he had his PhD on the abundance of chemical elements at different stars. This is not as a wide universe as the one he's studying today. Then he kept on as a post-PhD researcher at Durham University, but that was the beginning of a long path towards great success, working at many observatories, different institutions, and now he is working in the United States, across the ocean. Back in '83, he left Durham University and went to the Royal Observatory at Greenwich, the southern part of the UK, where as a student I had the pleasure of meeting him when I was working there as a trainee. In '85, back to Durham University, he stayed till 1993, where he took the chair as full professor at Cambridge University. Since 1993 till 1999, he kept at the most important levels, and now director of the Palomar Observatory and Caltech Observatories. Well, as you know, Professor Richard Ellis needs no introduction. He is an observational astronomer. And, well, the universe is like a big laboratory where there are physical processes and conditions that we cannot reproduce here on planet Earth. But we cannot design some experiences, we cannot repeat experiences. This is a unique experience, but we can develop devices, tools, devices to measure, to observe, and to retrieve data in order to conduct our studies. And that is a fundamental contribution by Professor Richard Ellis. He's been the driving force of the scientific development and technical development of avant-garde instrumentation and devices. He's got very many awards. I'm not going to mention this, but the Cosmology Award he received Peter and Patricia Gruber Foundation with his team back in 2007, and that did conduct to the experience on the acceleration of the universe and the existence of dark energy. One co-worker got the Nobel Prize, shared with other two astronomers for this huge contribution, and he's got the gold medal from the Royal Astronomical Society. This is a very important, unique award, and he is, as we see, been laureate by the British Empire as commander of the Order of the Empire. And, well, he's published many, many fantastic papers, but he's contributed to 30 PhD researchers as he's guided those experts that are now occupying the most important places worldwide. He must be, I'm sure he is, proud of disseminating knowledge and this transfer of knowledge that is so important. Nowadays, he's working in the field of observational cosmology, the origin and the evolution of galaxies, how they cluster into huge structures, the use of gravitational lenses. He is part of big joint programs studying the morphology of remote galaxies, a project of cosmology in the field of supernovae, and the study in the case of the earliest galaxies. And Richard Ellis promoted research worldwide, and now he is working at the construction of a 30-millimeter telescope, the TMT, where United States, Canada, Japan, India, China working together. This is a joint effort, different countries, different traditions, and this will be placed in Hawaii, and he will elaborate on this. And today he's going to talk about remote universe, the earliest galaxies, and, well, he will then talk about Let Be Light, finding the earliest galaxies. You have the floor, Professor Richard Ellis. It is a great honor and a pleasure to welcome you to our meeting.
Buenas noches. Good evening. Thank you very much to the Foundation for inviting me to give this lecture. I'd very much like to illustrate the work that we're doing in the distant universe. So the universe is a very big place, and light travels at a fixed speed. So when we look out in the night sky, we see the night sky as it was in the past. So when we look at the moon, we see the moon as it was just over a second ago. And when we look at the sun, we see the sun as it was 8 minutes ago. But things are very different when we use a big telescope. This image is the deepest image that we have from the Hubble Space Telescope. It represents an exposure of 10 days pointing at a small area of sky about 1/10 of the diameter of the full moon. And there are a large number of galaxies in this image, 2,000 galaxies at least. And the most distant objects that we see here are shown in these little squares, and we're seeing these galaxies as they were over 13 billion years ago, when the universe was only 3% of its present age. So it's long been a dream to travel back in time. Imagine you're a historian and you can go back and interview William Shakespeare and see whether he really wrote those plays. Or you could go back and actually witness the pyramids being built. You could see for yourself how the pyramids were being built. Well, astronomers are unique because they actually can time travel. This image is like a time tunnel, and we're seeing galaxies at various distances, and we're witnessing history directly. So when we look back in time, we're seeing the past directly. And of course, that's very exciting if we want to understand the evolution of the universe. We believe the universe began in a Big Bang 13.8 billion years ago, and the challenge of the astronomer is to piece together a picture of cosmic history. So astronomers don't think in terms of kilometers, and the numbers would be meaningless in a universe that's very large. So you can think of distance in two ways. You can think of it in terms of the time that the light has taken to reach you. We call that lookback time, and it's measured in years. So the universe today is 13 or 14 billion years nearly, and as we go back in time, the age of the universe is less and less. So here, the age of the universe is only 3 billion years old. And we can see galaxies from this remote past. But another way to think of history is that the universe is expanding. And the light from these galaxies has been traveling for such a long time that the universe has been evolving and expanding as the light ray has been traveling. So the universe was much smaller when the light ray left the galaxy, and now the universe is much larger. And the factor by which the universe has expanded, we call the redshift. And the redshift is what the astronomer can measure with a big telescope. Because the light has been expanded by the expansion of the universe, and the galaxy has been reddened and moved into a red region of the spectrum. And so this redshift can be a marker for how far back in time we are seeing an individual galaxy. So this is going to be an adventure it is an adventure with big telescopes. So the two telescopes that I use in Hawaii are the twin Keck telescopes. They have a primary mirror 10 meters in diameter, and a telescope has instruments, scientific instruments that we place. These two instruments are spectrographs, and we'll see that the spectrograph breaks the light of the galaxy so that we can identify this redshift that tells us how far away the galaxy is. This is an optical spectrograph. You can see a human being here, so you can see this is a very big instrument. This is an infrared spectrograph. These instruments are built in universities, but they're very expensive. A typical instrument like this is about $10 million and takes about 4 years to build. But we also use space telescopes. We use the Hubble Space Telescope, and this is central to my work. But there's another space telescope, the Spitzer Space Telescope, which works at infrared wavelengths, and we use that as well. And we use an instrument called the Wilkinson Microwave Anisotropy probe that looks after the glow from the Big Bang itself, and I'll describe that in a minute. So this is a short history of the universe. The universe began with a Big Bang, and we see the glow from that Big Bang as the microwave background radiation. This was discovered, and I'll explain in a minute, but this was discovered in 1965. Then the universe, at that point, is still dark. There are no stars or galaxies. And the theme of today's talk is really to find the moment when the universe was illuminated by stars and galaxies. And we sometimes call that moment cosmic dawn or first light. So let's start with the microwave background. So that's this glow from the Big Bang. It was discovered in 1965 by accident in New Jersey. In America, most people don't imagine that anything useful happens in New Jersey. But in this case, a big discovery was made in New Jersey with this telescope. And that led to a Nobel Prize. And then in 1992, we saw this glow from the Big Bang was not completely uniform. You can see there's structure. The temperature has ripples in the sky. And this is the beginning of the ripples are the beginning of the fluctuations that lead to galaxies and stars and you and me. So the universe is not completely uniform even at this time. And today the Wilkinson Microwave Anisotropy probe and a new satellite, European satellite, the Planck satellite, has given us beautiful detailed views of this glow from the Big Bang. We are seeing this glow when the universe was only 370,000 years after the Big Bang. So you remember Redshift. The universe at that time was so small that it expanded 1,100 times. Normally that radiation would be in the ultraviolet and optical, but it's been stretched so that it's seen at microwave frequencies today. So what happened next? So at this moment, we see the glow from the Big Bang, and the hydrogen atom has formed for the first time. But the universe is dark, and we call this period the Dark Ages. Now, astronomers are very good with names. We have dark matter, dark energy, dark ages. And the reason for this is it adds mystery to the subject. And it's very good for raising money If astronomers have mysterious problems to understand, then it's very good for getting funding. So the cold hydrogen is acting under gravity. Gravity is an attractive force, and gravity is beginning to bring these clouds of hydrogen together. And they collapse. And as they collapse, they get hot in the middle, and they heat up, and the temperature comes high enough for nuclear fusion. And a star is a fusion reactor. That's why how the sun shines. The sun is shining because hydrogen is burning into helium. And so suddenly we see these stars shining. And this is the moment of cosmic dawn. Now, we live in a universe, or we live in a world with theoretical astronomers. It's unfortunate, but they have a very detailed view of the universe. They don't need telescopes. They don't need observations. All they need is a computer. And one of my favorite theorists is Professor Loeb. And he has a very, well, he's from a very small university. You probably haven't heard of it, called Harvard. And he has a very detailed view of what happened during this period of cosmic history. So here, time is coming along here. Here's the glow from the Big Bang. Here are the dark hydrogen clouds, no starlight. Here are the baby galaxies. And these baby galaxies have very hot stars, and these stars are so hot that they break the hydrogen in space into a proton and an electron. You know, the hydrogen atom has a proton and an electron, and the starlight is so powerful it ionizes this hydrogen and creates these ionized bubbles. And these bubbles become more numerous, and today, in deep space, the hydrogen is completely ionized. So there are two problems that we have to understand. One is cosmic dawn. When did the galaxies begin? And the second is this ionization from neutral hydrogen to fully ionized hydrogen. And we call this process reionization. And Professor Loeb is a very clever man. He can tell us approximately when this happened, just from theoretical considerations. And it corresponds to a time when the universe was somewhere between 200 million years and 800 million years old. So that's quite a big gap, but that's as accurate as he can make it. That corresponds to a redshift 6 to 20. Now, I told you about the Wilkinson Microwave Anisotropy experiment. This experiment was designed to look at the glow from the Big Bang, but they found it was polarized. The Big Bang, the glow from the Big Bang is polarized, and this polarization is caused by electrons, and these electrons are the electrons from the hydrogen atom during this period. So unexpectedly, this satellite was able to confirm Professor Loeb's calculation that we need to look at this time between 200 and 800 million years after the Big Bang if we want to understand this picture of cosmic history. So I have a movie, a simulation of this reionization process. What you're looking at here is the dark areas. This is a box of space, and time is progressing. I've taken out the expansion of the universe, otherwise it would just get bigger. And this is the dark areas are the neutral hydrogen, and the blue areas are these ionized bubbles. And you can see, just like Swiss cheese, that this ionized regions begin to overlap and connect. And eventually, the universe becomes completely ionized. This is a very slow movie, but remember, this is a period of 200 or 300 million years. So I have sped it up a little bit just to make it easier for you to follow. So to understand this picture, we really need to study galaxies at great distances. And that is the theme of my talk, is to address these very simple questions. When did the Dark Ages end? And how quickly was it? Was it a very sudden moment? Was it dramatic? Or was it a slow process? And were the galaxies responsible for breaking the hydrogen back into a proton and electron? And perhaps the biggest adventure, can we find the very earliest galaxies, what we call the first generation galaxies? And beyond that, there would be darkness. So galaxy evolution is our subject, and galaxies in Madrid are big business. And the history of galaxies, to most people here, would mean the football team. But I'm not talking about the Galacticos. I'm talking about these kind of galaxies. So I like this slide very much because it sums up that we live in a universe that's evolving. Here are two galaxies as seen in the present universe. This galaxy is what we call an elliptical galaxy, and you can see it's very round. It has uniform color. There are no spiral arms, and in fact, it's very old. This galaxy is a spiral galaxy, and you can see it has blue, it's bluer color, it has a nucleus, and it has spiral arms. Now, if we go back to when the universe was only 5 billion years old, so that's 60% of the way back to the beginning, if you look at this galaxy, it looks like an immature version of this galaxy. It has a nucleus, and maybe it has the beginning of spiral arms. If you look at this galaxy, it looks a little bit like this galaxy. There are some galaxies that are irregular. We do see irregular galaxies today, but we seem to see more of them at this time. These are all pictures from the Hubble Space Telescope. If we go back to when the universe was only 2 to 3 billion years old, so that's 80% of the way back to the beginning, you can see the galaxies look very different. There are no spiral galaxies. They're very, very small physically. Some of them are multiple. It looks like they're merging. They're very complex structures. Now, how were we able to take these time slices? How did we know which galaxies were at which distance so that we could make this picture? So here's this idea of the redshift. If an object is moving away from you, the light rays are stretched. You've all heard this with the fire alarms on sirens in the street. So it is with the expanding universe. The light ray is traveling on top of the expansion of the universe, and the light ray is stretched. Now, a distant galaxy reveals a signal, a cutoff in the spectrum that occurs at a very fixed place, in this particular case in the ultraviolet. So if we take a picture of the galaxies in a red filter, in a green filter, and in an ultraviolet filter, the most distant galaxies will disappear. And so if you look at this galaxy here is present in the red filter, it's present in the green filter, and it's present in the ultraviolet filter. This galaxy is present in the red filter, present in the green filter, and it disappears. And it disappears because it's extremely distant, and it's been absorbed, in this case, by hydrogen. And so if we look at a patch of sky, we can find in blue all the galaxies which show this cutoff. These are very distant galaxies. It is a economic way of finding the very distant galaxies. And this was discovered, this technique was pioneered by one of my colleagues at Caltech, Chuck Steidel. And here he took an image with the Palomar telescope, and then he took spectra with Keck to prove that these galaxies were really very, very distant. So we have been using this technique with 3 filters. Steidel used the filter that cut off in the ultraviolet, but you can do this in the blue or in the infrared. And with this way, you go to more distant galaxies and you probe to earlier times. So here's an example of a galaxy seen at a redshift of 5. Here it is in one filter, another filter, and then it disappears. So by using this technique, in 2003, we had reached a new frontier in distance. We had been able to get to a redshift of 6, when the universe was 7% of its current age. And we were using these big spectrographs on Keck and measuring the hydrogen line in these galaxies to prove that they are indeed at this distance. So let me turn to Hubble. Hubble was doing all of the images for finding these galaxies, measuring their colors. So Hubble has been a very successful telescope. It is still in orbit. It orbits around 300 kilometers above the Earth's atmosphere, and it goes around the Earth in about 80 minutes. So of those 80 minutes, about 40 minutes per orbit is available for scientific exposures. So here's an image of a small patch of sky with an exposure time of 13 orbits. So that's about 8 hours. And here's a very deep exposure of the same area of sky, 400 orbits, much, much deeper. So if I just zoom in on this little patch here, you can see there's nothing significant in this little area here. But if I look at that area with the deeper exposure, then I uncover fainter galaxies. So this image is called the ultra-deep field. This was the deepest exposure that Hubble had taken at optical wavelengths in 2004. And so using this technique, we have been able to count the galaxies all the way back to when the universe was about 500 million years old. So this, if you like, is the number of galaxies that are shining against look-back time. So it reaches a maximum when the universe is about 3 billion years old. And then as you go back to the beginning, the number of galaxies is declining. So this is like a life cycle of the universe. We have birth, we have middle age, and we have decline. So the universe today is winding down. There are fewer galaxies shining, and that's because the hydrogen that is used to make stars is being exhausted. It's like an automobile running out of gasoline. But the exciting thing is, can we find the beginning? Can we actually look back far enough to see the beginning of galaxies? So Hubble has taken all of these deep images, and the first question I would like to address is, when did this dark ages end? Can we find the beginning of where there are pockets of gas which has not been ionized into protons and electrons? And this is where the Keck telescope has been very effective. So here on the summit of Mauna Kea in Hawaii are the 2 Keck telescopes. And my colleagues and I, my students and I, have done a big survey of over 600 galaxies using these color filters. to select these galaxies at different times. And we've pushed Keck to the very faintest limits. So we are now doing exposures with a big telescope like Keck of 8 to 12 hours, so 2 night exposures. And we see this glowing line of hydrogen, which is called the Lyman alpha line of hydrogen. And the number here represents the spectroscopic redshift, tells us how far away these galaxies are. These galaxies are so incredibly faint that we take these exposures of 2 nights to get these redshifts. So let me tell you how this works. In reality, we have graduate students, PhD students, whose theses, PhD theses, are involved in these programs. We physically go to the Keck Observatory with the student, and the students take the observations and are involved in this work. So one of the wonderful things about observational astronomy is a young student, can, for his or her thesis, address these very big questions in cosmology. This is one of my students, former students, Dan Stark. He got on the cover of Time magazine for his thesis. This was in 2006, and he was involved in these very long exposures here. This was one of my students who likes to observe in his pajamas, and here he is controlling the telescope directly. And so, a student can go to the telescope and observe and control the telescope directly. The bad news is, of course, a telescope is on the ground. So unlike Hubble, you can be allocated time, and then it's cloudy. So last year we had 5 nights on the telescope, and every night was cloudy. And so the job of the professor is to cheer up the students and make sure that they don't get depressed and give up and go and move into commerce or banking or industry. And this photograph was taken in the middle of this cloudy night run after I had bought the team 2 bottles of wine. And you can see that the photograph is very slightly blurred. So the thesis, my latest student, Matt Schenker, this guy here, his thesis addresses this question of when did the Dark Ages end? I told you about this glowing line of hydrogen. It is a very famous line in atomic physics called the Lyman alpha line. When you have a galaxy with hydrogen and you have hot stars, the stars heat up the hydrogen and this hydrogen glows. And it glows primarily in this line. So we would expect most galaxies to show this strong line. And that's what these lines are here. But this line can be destroyed if the galaxy is sitting in pure hydrogen, in a region which contains nothing but hydrogen. So if a galaxy is sitting in pure dark hydrogen, then this line is destroyed. The galaxy has to be sitting in one of these ionized bubbles for this line to escape. So I have a little analogy for you to explain this experiment. You're on the motorway and you're looking back in time. Every star, every galaxy is an automobile, and it is glowing in this hydrogen line, and those are the headlights of the car. But as you go back to the Dark Ages, there's a fog. The cars are in the fog, but you can't see the headlight because the line can't get out it can't penetrate the fog. So we would expect, as we go back into the Dark Ages, that this line would become less prominent. And that's what my student has found. He has found that the fraction of galaxies showing this line increases as you go back to about 60%, but then as you go a little bit further, it starts to drop. And it starts to drop because we're entering that foggy period when the universe is dark. The galaxies are penetrating, are unable, the shining light is unable to penetrate through this fog. So here are the emitters at this point, and we only found 3. So we found 60% of them here, but we only found about an eighth of them, 12% or so, at this point here. And this work has since been corroborated by other observers. So let's go back to Hubble. In 2009, Hubble had a new instrument installed using the space shuttle. And this is called the Wide Field Camera. It is an infrared camera, and it's 40 times better than its predecessor. So let me show you. This is a picture taken with the new camera, 16 orbits. This is a picture taken with the old camera, 72 orbits. So if you just look at a patch here, maybe, 72 orbits old camera, 16 orbits new camera. You can see it's much deeper. It's actually sharper. If you look at this little double object here, you can see the images are sharper as well. So the first thing that the Space Telescope, Hubble Space Telescope, did when this new camera was installed was to go to that same deep field, remember the ultra deep field, and take a 10-day exposure in this ultra deep field. And the director of the Space Telescope Institute told everybody that he would release this data on a particular day in September 2009. So everybody was waiting for this data. It was publicly available. So teams, rival teams, were writing papers, scientific papers, without the data and leaving spaces in their paper for the figures in the scientific paper. So when the data came out, there was an explosion of papers from this data. There were all of these articles, 12 articles in 4 months, and in fact 4 papers within 10 days. So let me tell you what we found from this wonderful camera. Last year we went back to this field and we exposed a further 128 orbits, about 5 days or so. And this is a very small team involving astronomers in Scotland, Japan, Paris, and Arizona. And this is that image that you saw at the beginning of my talk. This is now the deepest infrared image that we have, and it shows these extraordinarily distant objects. So for the first time, we pushed the frontier to a redshift of almost 12, when the universe is about 380 million years old. And it's the same technique. So you see a galaxy here, 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 and then it disappears. Galaxy here, 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 and it disappears. These galaxies are admittedly extremely faint. I would never have imagined, even 5 years ago, that we could see objects this distant or this faint. Now, there is another technique for finding these extraordinarily faint galaxies, and it originated with this gentleman here, who needs no introduction. My wife gave me a calendar, an Einstein calendar one year. You know, that every month had a different picture of Einstein. You know, there's Einstein with the blackboard, Einstein on a bicycle. By the time I got to April, I realized he was always wearing the same suit. And I think maybe he only had one suit. So Einstein predicted that light can be bent by massive objects. So just as we use an optical lens to magnify, reading when we're using a magnifying glass, so we can have lenses in the sky that magnify distant objects. And this is called gravitational lensing. And so we can boost the signal of these very faint objects. It's an interesting story. The discovery of lensing involved a very famous astronomer, Eddington, in Cambridge, who was so inspired by gravitational lensing. He was a theorist, but he very sensibly became an observer and proved that Einstein's theory was correct. And this lensing was the primary reason that Einstein became famous. So here's a movie of a gravitational lens. So this is a simulation of a dark lens moving across one of these deep fields. And you can see that depending on the alignment between the background object and the lens, you can get spectacular magnifications of 50 to 100. So it's like a free telescope, like having a telephoto lens on the end of your telescope. The problem is you can't point this telescope anywhere. You can only point where there are these clusters of galaxies. So when I got to Caltech, we used this technique for many years. This is very faint, but there are two images here of the same galaxy. This is at a redshift of 5.6, and it's magnified by a factor of 30. Then a few years later, for a brief moment, we had the most distant object. This is at a redshift of 6.8. It is three images, A, B, C, of the same object, magnified by a factor of 25. And this has now become a traditional way of finding distant objects. And the record at the moment, this is not my work, is three images, 1, 2, 3, of a galaxy at a redshift of 10.7. So there are these two techniques: expose with Hubble for a very long time, or look through clusters of galaxies that act as big, powerful gravitational lensing. And the good news is the two techniques agree. If we remember that diagram where the number of galaxies is declining, we've now pushed the frontier back to when the universe was only 350 million years old. And although there's still a lot of uncertainty, there's a very smooth, overall a smooth decline. It's continuing. So this would suggest that there are maybe galaxies just a little bit further back in time as well. Now, I didn't spend 128 orbits with Hubble just to find 7 galaxies. If we come back a little bit closer, we found 74 galaxies with redshifts between 6 and 9, the largest catalog of galaxies at that time. And that allows us to look at how many luminous galaxies there are and how many feeble galaxies there are. So there are luminous galaxies and feeble galaxies. And one of the main results of this new deeper data is that the sky is ablaze with the feeble objects. At this time, most of the light is coming from very, very low mass galaxies that are very numerous and very, very feeble. We don't see these galaxies today, so they must have merged with one another to make bigger galaxies. We can also look at the colors of the stars in these galaxies to see whether they genuinely are very, very young galaxies at cosmic dawn. And perhaps the bad news is they're not. They are not extremely blue, such as would be the case if they were very, very young indeed. We think they're about 100 million years old. And so what this means is that the birth of galaxies was probably around a redshift of 15, maybe 200 million years after the Big Bang. Now, unfortunately, we've reached the limit with Hubble. We cannot go any deeper or further into the past with Hubble because Hubble has no more filters that we can use to locate the objects. There is one other space telescope, the Spitzer Space Telescope, and that is still in operation. It is a very small telescope, 85 centimeters, but it is looking at old stars and measuring the ages of the galaxies. So the combination between Hubble, which looks at the young stars, and Spitzer, which looks at the old stars, is very, very powerful. And Spitzer also predicts that we expect to find galaxies just beyond the limit that we have seen with Hubble. So we can piece a story together that I think just about works. We can look with Hubble at the history of star formation, and we can predict from that how we see the old stars rising with time. And we can predict how the universe went from being completely dark at a redshift of 15 to 20 to being fully ionized at a redshift of 6. And these electrons can then produce the polarization that we see in that Wilkinson Microwave Anisotropy experiment. So there's almost a picture that works, but we haven't yet found the very earliest galaxies. It's just a little bit further back in cosmic time. So we look to future, more powerful facilities to continue the story. The James Webb Space Telescope is a 6.5-meter successor to Hubble. It is being launched in 2018, and it will be able to go back into this period, beyond the limit of Hubble. So it will explore this era very, very well. It will also have the power to measure the composition of these galaxies. Now, a first-generation galaxy will not have heavy elements like oxygen, magnesium, silicon, and iron. All of those heavy elements are made in stars. Only hydrogen and helium are made in the Big Bang. So a first-generation galaxy will not have these chemical elements. Here are strong lines of oxygen that we will be able to detect with the James Webb Space Telescope. So we will have the capability of measuring the chemical composition of these galaxies to see whether they're the very earliest generation of objects. And then on the ground, we will have giant ground-based telescopes. As Professor Diaz mentioned, I'm involved in the 30-meter telescope. I hope that's obvious. It's a 30-meter aperture. So it will be 9 times more powerful than the Keck telescope. It is a partnership between my university, the University of California, Canada, Japan, China, and India, a big adventure in sociology and politics, as well as money, technical dynamics, engineering, site testing, everything. A global telescope. And then here in Europe, the European Extremely Large Telescope, even bigger. It had to be bigger than the American telescope, 39 meters. The two telescopes will be in different hemispheres, so they will complement each other very well. Now, these are very expensive facilities, and often people ask, why is it necessary to spend so much money on science? And let me just point out, firstly, before answering that question, the technology that makes this possible was pioneered on Keck, and that is the segmented mirror. So these mirrors can be made so large because they're not a single piece of glass. So Keck is composed, the Keck mirror is composed of 36 1.8 meter segments. The 30-meter telescope will have 492 1.4 meter segments. So back to this question of cost. These are so expensive, such expensive facilities. So let me just remind you that, are these projects worth it? So let me tell you that TMT is worth 9 footballers. Okay, admittedly so I'm Welsh, so Gareth Bale is my hero, but only 9 Gareth Bales would pay for the 30-meter telescope. Gareth Bale will play soccer for 5 years as a star, and then his career will be finished. The 30-meter telescope will last for 50 years and do wonderful science for... The ELT is a little bit more expensive. You need 12 Gareth Bales for this. So on that note, let me end with Edwin Hubble. So Edwin Hubble, of course, a very famous astronomer. He discovered the expansion of the universe. We named the Hubble Space Telescope after him. A very interesting man, not very popular with his scientific colleagues, actually. And he was an American, but he had an affected British accent, which they didn't like in America at all. But he was an extremely good writer and speaker. And in 1932, he went to Yale University and gave a series of lectures, which he wrote up in a book called The Realm of the Nebulae. It's a very famous book, just been reprinted, actually. And in that book, there is this quote: "At the last horizon, we search among ghostly errors of observation for landmarks that are scarcely more substantial. The search will continue. The urge is older than history. It is not satisfied, and it will not be pressed." Thank you very much.